Welcome back to the classroom. My name is Mr. Wong. So today we're going to go through another HSC paper or question from the HSC. This is to answer Module 6, Inquiry Question 2, which is all about the motor effect. So let's dive into the question and let's also try and solve for it. I'm going to use a highlighter to just underline any key points of the question, so I'd suggest you to do something similar. We have a single turning coil positioned in a region of a uniform magnetic field which has a strength of 0.2 Teslas. The plane of the coil is at 45 degrees to the magnetic field. The coil is a square 5 centimeter size and carries a current of 10 amps. Question says, calculate the magnitude of the force on side AB. So the formula we're using is F equals to Bill. Okay. So what we need to work out here is whether or not the magnetic field is coming at this Y here at right angles or at an angle of 45. Well, it's actually coming at an angle of 90 degrees, so it's nice and perpendicular, so we should expect a maximum force appearing. Some people might be wondering, why is it not 45? Let's say if it's like at these angles here, at all points the Y is meeting the magnetic fields at right angles. So say if I was to look at this side on, so if I drew my eyeball here, I'm looking at dead set flat on that, okay, on that side, I'd see the wire, see B to A, and I'd see the magnetic field, if I could actually see it, it's cutting it at a 90-degree angle. So I don't need to use sine theta in this calculation, I just need to use BIL, okay? And for BIL, B is the strength, which is 0.2, I is the current, which is 10, and L is our length, which says 5 centimeters. That needs to be converted into meters. That's our SI units. And so 5 centimeters is the equivalent of 5 times 10 to the power of minus 2 meters. Now all we have to do is put it into the calculator. Okay, so the answer I get is a force of 0.1 newtons. And that's the amount of force that's being applied onto our wire AB. Let's move on to our second question. And this one, it says, explain why the net force produced by the magnetic field on the coil is 0. Okay. So let's have a look at this diagram again. I'll switch colors. Okay, so our coil, if you actually have a look here, might need to just rub out some of these diagrams here. Having a look back at our coil. So it looks like it's rotating, going on both sides here. Okay, well, you think of it this way here. This is a wire, okay? This is a wire. Let's say the current is coming from here, coming out from here, okay? If the current comes up here and then comes down here, what we know is the wire has equal length on both sides. So the force being applied on both sides is the same. Now, if I actually have a look, if I use the right hand palm rule, so to speak, so using my right hand palm rule, let's look at where the force is pushing this side of the wire. So right thumb up and fingers pointing to the right hand side. So the force exerted on this side, obviously the direction of the current doesn't actually matter. It doesn't matter if it's coming up or down here, but we'll just make it like that. It's going into the page here, and if I did this exact same thing for DC over here, thumb pointing down, right thumb pointing down, right hand fingers pointing to the right, my palm is facing outwards. So one's going in, one's going out. Now, if you think about it, they're two opposite forces. However, we already stated that the force that they experience is the same. So equal opposite forces. So I'll just write that down. Equal opposite forces leads to cancelling out. So that's why there's a net force of 0 on AB and DC. If we did the exact same analysis for AD and BC of similar sorts, you would see the exact same thing. So you can have a go at testing with your right hand palm rule out, and you get the exact same result. So that's why there's a net force of 0 on this coil here. Okay, so let's just start by using the individual wires. So on wires AB and DC, they have the same magnitude of force. However, the forces are moving in opposite directions. Of each other, and as such cancel each other. And then we can also say the same applies for sides AD and CB, as the currents are moving in the opposing directions of these wires. Okay, so probably didn't word it as succinctly as I should have, but what you can say is the reason why there is a net force of 0, so hence net force on coil is 0. So let's break this back down again, and I'll make it nice and clear. The reason why the net force on the coil is 0 is because on the opposing sides of those wires, they have the same amount of force. However, the force is moving in the opposite direction, cancelling each other out. The reason why the forces are moving in the opposite direction, or in the opposite direction to each other, is because the current on the opposing wires are moving in the opposite direction. The current is the same on both sides, but it's moving in the opposite direction, and hence why the forces are also moving in opposite direction, causing them to cancel each other out. Okay, and that's how you approach this question. If you found this explanation useful in developing your understanding of the motor effect and analyzing these kind of data questions, please hit that like and subscribe button, and I'll see you next time.